what truly threatens the future of our species. A profound threat to our existence hangs silently above. We perceive Earth as a safe haven, but in reality, our planet is speeding at 67,000 miles per hour through a crowded cosmic intersection. Racing through the dark with us are millions of ancient rocks following the cold laws of orbital mechanics. On impact, this 200 million-ton Titan delivers more fury than every nuclear warhead humanity has ever built. It would unleash a force capable of darkening the sun and altering the course of civilization in a single day. We assume we are secure, but Earth bears the scars of thousands of past collisions, and the evidence is lying right beneath our feet. So if the danger is so frequent, why do we see so few craters? The answer lies in the fact that the Earth does not advertise its violent history. Unlike the Moon, whose pockmarked face serves as a permanent record of cosmic bombardment, our planet is a master of disguise. Erosion, vegetation, and tectonic activity constantly scrub the surface clean. But there are some wounds too deep to heal. In the high desert of northern Arizona, there is a scar that refuses to fade. It is a hole in the ground nearly 1 mile wide and 550 feet deep, large enough to swallow 20 football stadiums simultaneously. For decades, this depression was a source of fierce debate. Early geologists looked at the shattered landscape and concluded it was the result of a volcanic steam explosion. It was a logical assumption. The region is dotted with ancient volcanoes. But there was a problem with the volcanic theory. There was no volcanic rock. Even stranger, there was almost no sign of the giant meteorite that supposedly made the crater. If a rock from space had dug this hole, where was the rock? The answer lay not in geology, but in high-velocity physics. 50,000 years ago, this desert was a temperate wooded plain where mammoths and giant sloths roamed. Then the sky split open. A nickel-iron asteroid, roughly 150 feet across, slammed into the limestone bedrock at 50 times the speed of sound. At that velocity, the laws of mechanics break down and the laws of fluid dynamics take over. The rock did not simply punch a hole in the ground. Upon contact, the immense kinetic energy stored in the asteroid's motion, traveling at nearly 40,000 miles per hour, was instantly converted into heat. In a fraction of a second, the solid asteroid and the rock beneath it did not just melt, they vaporized. They were transformed instantly into plasma, a superheated gas expanding outward with the violence of a nuclear warhead. The crater wasn't dug, it was blasted open. A fireball brighter than the sun expanded upward, launching a cubic mile of pulverized rock into the stratosphere. The shockwave leveled forests for miles, crushing every living thing within a 50-mile radius, before the sound of the impact even arrived. The reason scientists couldn't find the asteroid was that it had annihilated itself in the explosion, but the impactor left a distinct signature. It wasn't the crater itself, but what was hidden inside the microscopic structure of the rocks. When geologists like Eugene Shoemaker finally examined the sandstone at the site, they found something that volcanic activity could never produce: shocked quartz. Under a microscope, a quartz crystal usually looks like a clear, unbroken lattice, but the quartz found in Arizona was crisscrossed with microscopic fracture lines called planar deformation features. To create these fractures, you need pressure. Not the slow, heavy pressure of a mountain building, but a sudden, violent shock wave, delivering millions of pounds of pressure in a microsecond. On Earth, only two things can generate the energy required to shatter the atomic lattice of quartz. In this way, a nuclear explosion or a hypervelocity impact from space. The discovery of shocked quartz was the smoking gun. It proved that the Arizona crater was not a geological hiccup, but a ballistic wound. Yet, in the grand scheme of the cosmos, this event was merely a warning shot. The rock that hit Arizona was small, a pebble, compared to the boulders lurking in the dark. It destroyed a region, but the planet survived. To find evidence of a truly catastrophic impact, we must look deeper, as nature excels at obscuring these geological scars. The Arizona crater is terrifying because it is visible, but the true horror of our cosmic neighborhood lies in what we cannot see. If a rock 150 feet wide can devastate a landscape, what happens when a rock 10 times that size strikes logic dictates that the Earth should be covered in massive craters. Yet when we look at a satellite map, we see mostly oceans, forests, and cities. Where are the giant scars? To answer that, we must travel to the quiet cornfields of Manson, Iowa. On the surface, Manson looks like any other small town in the American Midwest flat, fertile and peaceful. But deep beneath the soil lies a secret structure that defied explanation for nearly a century. As far back as 1912, water well drillers noticed something strange about the geology here. The water was soft, unlike the hard water of the surrounding region. But it wasn't until the mid-1980s that geologists Ray Anderson and Brian Witzke began a series of deep core drillings that revealed the terrifying truth. As the drill cores were pulled from the earth, the geologists realized they were looking at a geological impossibility. In a normal stratigraphic column, layers of rock are stacked like a history book, younger rocks on top, older rocks at the bottom. But the Manson cores were a chaotic jumble. They found fragments of granite rock that belongs 10,000 feet deep in the crust, mixed with sedimentary rock from the surface. The layers were inverted, shattered, and fused together. It was a site of profound geological disruption. The stratigraphy of Manson had been completely churned and mixed. When they placed these samples under a microscope, they found the signature shocked quartz. But they found it in rocks dating back 75 million years. The scale of the deformation suggested an explosion that dwarfed the Arizona event. This wasn't a warning shot. This was a strategic bombardment. 75 million years ago, a chondrite asteroid, roughly 1.5 miles in diameter, 50 times larger than the Arizona rock, screamed into the Cretaceous atmosphere. When it struck Iowa, it released energy equivalent to 100 million megatons of TNT. That is 10 times the combined explosive power of every nuclear weapon on Earth at the height of the Cold War, detonated in a single second. The explosion would have been visible from space. The asteroid punched through the crust, penetrating miles deep before vaporizing. The resulting crater was 24 miles across a hole so vast it would dwarf the Grand Canyon. The blast wave flattened the entire region, and the plume of vaporized rock and steam shot into the stratosphere, blanketing the hemisphere in dust. It was a localized apocalypse, a city killer, long before cities existed. So why is there no hole in Iowa today? Why do farmers plant corn on top of ground zero? The answer is the Earth's astonishing ability to heal or hide its injuries. In the eons following the impact, North America was subjected to the relentless grinding of the ice ages. Massive glaciers, miles thick, advanced and retreated across the landscape like industrial sandpaper. They scoured the surface, shaving off the crater walls and filling the deep depression with hundreds of feet of glacial till gravel, sand, and soil. By the time humans arrived, the Manson crater had been completely obscured by glacial deposits. The devastating evidence was hidden beneath a flat, serene landscape. It serves as a chilling reminder the Earth has been hit before by civilization-ending rocks. And the only reason we don't see the evidence is that time has erased it. We inhabit a landscape shaped by ancient impacts, often unaware of the geological history beneath the surface. But Manson was not the worst of it. 10 million years after Iowa burned, the solar system reloaded. The next rock in the chamber wasn't a city killer. It was a planet killer. And when it arrived, it didn't just leave a scar. It reset the entire evolutionary timeline of Earth. To truly grasp what happened 65 million years ago, we must stop analyzing statistics and start experiencing the reality. We must place ourselves at ground zero. Imagine you are standing on a tropical beach on the Yucatan Peninsula in 65,000 BC. The world is lush, humid, and teeming with life. But high above the atmosphere, a mountain of rock, 6 miles wide, the size of Mount Everest, is falling silently toward the Earth at 40 times the speed of sound. It moves so fast that it tears a vacuum in the sky. If you look up, you don't see a streak of light. You see a second sun appear instantly brighter than the first. It swells in the blink of an eye from a star to a blinding sphere that consumes the horizon. There is no sound. The object is moving far faster than sound waves. There is only a flash of light so intense it incinerates your retinas before your brain can process the image. Then contact. When the leading edge of the asteroid strikes the shallow waters of the Gulf of Mexico, the trailing edge is still 35,000 feet up in the atmosphere, the cruising altitude of a modern jetliner. In that single instant, the asteroid connects the ground to the edge of space. It doesn't crash. It penetrates the Earth's crust, unleashing an explosion equivalent to 100 million megatons of TNT, more energy than 6 million volcanic eruptions occurring simultaneously. You are vaporized instantly. The shockwave, moving at Mach speeds, atomizes the water, the bedrock, and the biological matter, turning the region into a rapidly expanding plasma fireball. But the true horror is for those who survived the initial seconds. The impact punches a hole in the atmosphere, launching trillions of tons of vaporized rock and glass halfway to the moon. This is the ejecta curtain. For a few minutes, debris hangs in the void. Then gravity takes hold. As trillions of glass-like beads re-enter the atmosphere, friction turns them into flaming meteors. The sky fills with fire. The entire atmosphere begins to glow with an intense infrared heat. This is the broiler effect. The atmosphere acts as a global infrared radiator, transmitting immense heat to the surface. Thousands of miles away, air temperatures spike drastically. Dry vegetation spontaneously ignites, triggering wildfires worldwide. Surface animals succumb to the extreme heat. It is a catastrophic event for the biosphere. Within hours, the fires burn out, but the devastation has only begun. The asteroid hit a region rich in sulfur, releasing colossal amounts of sulfur and carbon dioxide into the stratosphere. Combined with soot from global fires, this forms a suffocating shroud around the planet. The sun vanishes. A darkness deeper than night envelops the globe for months. Without sunlight, photosynthesis stops. Plants die. Herbivores starve. Carnivores turn on each other before fading into history. The food chain doesn't just break, it dissolves. This is the impact winter. Temperatures plunge, freezing the scorched planet. The oceans turn acidic, collapsing the marine ecosystem. By the time the dust settles, 75% of all species have been wiped out. The dinosaurs are gone. The planet is silent save for the scurrying of small rat-like mammals emerging from their burrows to inherit the ruins. How do we know this happened? The proof lies hidden in the rock record, waiting for forensic detectives. Evidence can be found in places like Trinidad, Colorado. If you look at the canyon walls, you see layers of rock teeming with Cretaceous fossils. But then there is a sharp line. Above this boundary, the fossils disappear. This is the KT boundary. Sandwiched between the ages is a layer of white clay, barely an inch thick. In 1980, scientists Luis and Walter Alvarez analyzed this clay and found a chemical anomaly that changed science iridium. Iridium is extremely rare on Earth's surface, but common in asteroids. The Alvarez team found levels nearly 200 times higher than the norm in this layer. This was the extraterrestrial fingerprint dust from the asteroid settled over the entire globe. Alongside it, they found shocked quartz confirming a single, massive impact had enveloped the planet. The KT event teaches a humbling lesson. We exist because of a cosmic accident. If that asteroid had arrived 20 minutes later, Earth would have rotated slightly, and the rock might have splashed into the deep Atlantic, absorbing the energy and potentially sparing the dinosaurs. We mammals would still be scurrying underfoot. The impact was the crucible of human evolution. But there is a twist. The same lottery that allowed us to evolve could also extinguish us. The dinosaurs didn't have a choice. They didn't have a space program. We do. But are we watching the skies closely enough? For most of human history, asteroid impacts were viewed as abstract concepts, ancient events confined to the deep past. We believed the solar system had settled into a clockwork rhythm of stability. That illusion shattered in July 1994. The warning arrived a year earlier when asteroid hunters David Levy and the Shoemakers discovered a comet near Jupiter. Named Shoemaker-Levy 9, it was no ordinary object. Jupiter's immense gravity had torn it apart into a string of pearls, 21 fragments marching in a line. This revealed a critical secret. Many cosmic bodies are not solid monoliths, but rubble piles easily disrupted by gravitational shear. Skeptics shrugged. Some predicted the impacts would be invisible, like a mosquito hitting a truck windshield. Nature had a different plan. When Fragment G slammed into the Jovian atmosphere, it was traveling at 140,000 km/s. It didn't just burn up, it detonated. The kinetic energy transformed into a fireball so massive, it created a tunnel of fire through the cloud tops. The explosion released energy equivalent to 6 million megatons of TNT, hundreds of times the world's nuclear arsenal. Humanity watched in awe. The impact left a dark bruise on Jupiter's face, the size of the Earth. It lingered for a year, a black eye staring back at us across the solar system. As Levy noted, it was a live fire demonstration. It showed exactly what happens when a planet gets in the way of a cosmic bullet. The shock of Jupiter kick-started a new era of vigilance. NASA funded programs like Linear to scan the skies using high-tech observatories to hunt for the one star that moves. But the sky is vast, and our eyes are few. In March 2004, the system was tested. Researchers at Linear spotted a faint streak of light. It was a rock roughly 100 feet across, small compared to the dinosaur killer, but large enough to level a city like London in a Tunguska-style airburst. They named it Asteroid 2004 FH. Then they calculated the orbit. It wasn't years away. It was 48 hours away. While the world went about its business, unaware of the danger overhead, 2004 FH screamed past the Earth. It didn't just pass the moon, it threaded the needle, passing just 26,000 miles above the surface. To put that in perspective, that is inside the orbit of our telecommunications satellites. It was a near miss that passed within the immediate vicinity of our planet. We tracked it, but only at the last second. This highlights the terrifying blind spot in planetary defense. Telescopes rely on reflected sunlight. If a rock approaches from the direction of the sun or is made of dark carbon with low albedo, it becomes an invisible stealth bomber. Furthermore, these rocks drift. A phenomenon known as the Yarkovsky effect occurs when the asteroid absorbs sunlight and re-radiates it as heat. This acts like a tiny thruster, pushing the asteroid off its predicted course. A rock calculated to miss us today might drift into a collision course tomorrow. We have identified about 90% of the large asteroids capable of global devastation. However, of the millions of smaller objects capable of regional destruction like 2004 FH, we have tracked less than 1%. The question is not if another impact will occur, but whether we will be prepared to intervene when it does. When faced with an incoming asteroid, our instinct, fueled by disaster movies, is to hit it hard. We imagine launching a nuclear warhead and detonating the rock into dust, saving the day in a blinding flash of glory. Physics unfortunately disagrees with Hollywood. The problem lies in the structural integrity of the enemy. We assume asteroids are solid monoliths, but recent missions reveal that the most dangerous objects are often rubble piles, loose aggregations of boulders and dust held together by nothing more than weak gravity. Planetary scientist Eric Asfog demonstrated this counterintuitive reality. If you fire a projectile at a solid rock, the shockwave travels through it, cleanly shattering it. But if you fire at a rubble pile, the energy is absorbed. The shockwave dissipates through the gaps between the rocks, a property known as macroporosity. It's the difference between shooting a glass bottle and shooting a sandbag. The sandbag absorbs the bullet. Simulations indicate that a nuclear detonation against a rubble pile structure can yield counterproductive results. Due to mutual gravity, the scattered fragments tend to drift back together, eventually reaccumulating into a single mass. Alternatively, the explosion could fracture the object into a cloud of radioactive debris. Consequently, Earth would face impacts from numerous hazardous fragments across a wide area rather than a single concentrated entry. To successfully divert a rubble pile asteroid, high-energy impact is often ineffective. We require a method of precise, low-force intervention. If we can't blow them up, we must move them. The new philosophy of planetary defense is deflection. We don't need to push the asteroid thousands of miles off course. We rely on the gravitational keyhole. Earth and the asteroid are both moving at incredible speeds. To avoid a collision, we simply need to change the asteroid's arrival time by a few minutes. If we can slow the rock down just enough, Earth will have moved out of the cross street by the time the asteroid arrives. Former astronaut Rusty Schweickart has proposed an elegant solution, the gravity tractor. We launch a heavy spacecraft and asteroid tugboat to rendezvous with the rock. It never touches the surface. Instead, it hovers nearby using its own tiny gravitational attraction as a tow rope. By firing its thrusters to maintain a constant distance, the spacecraft gently pulls the asteroid. It is a faint tug, barely the weight of a sheet of paper. But applied over years, it can change the asteroid's velocity just enough to miss the Earth. It avoids the rubble pile problem entirely because it pulls the entire mass at once. Another solution comes from J. Melosh, the solar mirror. By deploying a massive mirror in space, we focus the sun's rays onto a specific spot on the asteroid. The intense heat vaporizes the rock, creating a jet of gas that acts as a natural rocket thruster. The asteroid essentially pushes itself off course using its own mass as fuel. These technologies, along with kinetic impactors like NASA's DART mission, prove that unlike the dinosaurs, we have the engineering capacity to intervene in our own extinction. But they share one fatal requirement: time. A gravity tractor needs years to work. A solar mirror takes decades. If we discover a rock on a collision course 6 months from now, these elegant solutions are worthless. We would be left with the nuclear Hail Mary. The ultimate variable in the equation of survival is not energy or mass. It is early detection. We can stop them, but only if we see them coming. We live under a comfortable illusion of permanence. We build cities and plan for the next century, assuming the sky above is empty. However, the geological records in Arizona and Iowa reveal a reality. Earth is not isolated. It orbits within a densely populated solar system. Planetary history is defined by dynamic collision events. The dinosaurs ruled for 150 million years, yet they were wiped out in a single afternoon, victims of a cosmic lottery. They couldn't escape. We are different. For the first time in 4.5 billion years, a species possesses the intelligence to calculate the odds and the technology to change them. We are the first species capable of identifying a planetary threat before impact occurs. We possess the engineering capability to deflect the object, converting a potential global catastrophe into a safe flyby. But capability is not action. Millions of rocks drift in the dark, governed by gravity's cold equations. One is certainly on a collision course, perhaps hidden in the sun's glare, racing toward us right now. The clock is ticking. The difference between us and the dinosaurs is choice. They died because they didn't have a space program. If we follow them into extinction, it won't be because we lack the ability to save ourselves. It will be because when the sky offered us a choice, we chose to look down instead of up. The threat is inevitable. The question is, are we maintaining our vigilance?